Let's take a look at week 10, example 7. This is our Ferris wheel application problem. Before we get started, I'd actually like to point out I really like Ferris wheel problems. I've even got my family Ferris wheel down here. I was actually raised on a traveling carnival. My parents own carnival equipment. That's actually the family Ferris wheel right there, which you can't see in this picture, is at the center of the Ferris wheel. It actually says my last name in the middle right there. If you don't believe me, then you can go to lures.com right there and you can see the family carnival website right there. In fact, there's still a few pictures of me from about 10 years old and some of the food stand pictures in there as well. What we're interested in doing here for the trigonometric problem here is we need to determine an equation that's going to represent a person's height that's been riding this Ferris wheel for t seconds. Then we want to use Desmos to help us identify some values of interest that are associated with the heights on the Ferris wheel. So what we're going to do on the whiteboard is come up with our equation, then we'll pop over into Desmos to find some values here. So the only information that we've been given is that the diameter of the Ferris wheel is 250 feet. We've been given that it is going to complete one revolution every 40 seconds. So here is my Ferris wheel. It's on its two posts right there. And what I know is that the total height it's going to traverse is 250 feet. And it's going to take 40 seconds to do that. So we want to remember for ourselves that we're generally trying to build an equation of the form it looks like this here. Remember that we have our amplitude that affects how high and low we go from our midline. We have k, which represents our midline, which height is the center of our sine or cosine graph going to be. Omega is going to help handle our period information, and phi will help us do any horizontal shifting here. I've generally written this as sine because these are sinusoidal equations, but it's certainly the case that we might choose to use a cosine here in this case. For our purposes here, I'm going to use some slightly different letterings as well. I am going to use t to represent time in seconds since the person has stepped onto the Ferris wheel, but I'm going to use h over here using some function notation instead to help represent the fact that this is height based on time. And so what we'd like to do is come up with this h of t sinusoidal equation that's going to help model this guy over here. So let's think about what our pieces should be. Let's start with some of the easier ones, a and k, then think about omega, and then let's think about what function do we actually want to use here. So the first thing that I might recognize for myself is that the midline, where should all of our values sort of in a sense have an average value of, where's the middle of our heights that we're going to experience. And what I can see is if the total height traversed is 250, then half of that should be the midline. So our midline should be 250, half of 250 is 125. That's going to be the mid value here. We're going to go from a low of 0 to a high of 250. 125 is right in the middle. If we're centered at 125, the question, what is the amplitude, asks the question, how far do I go up and down from 125 to get up to 250 to get down to 0? Well, it turns out the amplitude then is also going to be 125. From a height of 125, I need to go an additional 125 further to get to the top. I need to go 125 lower to get to the bottom here. So our amplitude here should also be 125. We want to remember that our formula to find the omega term here, this is helping us out with our period. Since this is going to repeat every 40 seconds, we saw that our general formula here was 2 pi divided by t, where t is how long it takes for one period to be traversed. So for our purposes here, this should be 2 pi divided by 40. And I also want to know what function should I actually be using here. I wrote my general form as a sine function, but I am not necessarily convinced that should be the case. The thing that I'm aware of is that on a Ferris wheel, you are always going to get on at the bottom, at the minimum height that you ever experience. I know that the sine function always begins at its midpoint, so it doesn't seem like I want to use sine. I know that the cosine function begins at its maximum. We are interested in beginning at our minimum, so I'm going to go ahead and use the negative cosine function here. Since we are beginning at our minimum height, I don't need to include any phase shift information. I do want to point out that this is like an example in the textbook. It's something like number like 57 or something like that. They, instead of using the negative cosine function, they use the positive sine function with a phase shift to help accommodate for the fact that sine would be starting here, negative cosine starts here. So they do a phase shift of like pi halves or something to account for that 90-degree difference of starting location. I generally try to avoid using phase shift terms whenever possible. To me, it's simpler to understand the concept of using the negative cosine function than it is to manage any of my phase shifts right there, which is why I choose this. So I think we're ready to actually form the equation we're interested in here. We're going to use the negative cosine function with an amplitude of 125. I know that omega is going to always be 2 pi divided by the period length, so that's 2 pi over 40. I don't need to include any phase shift ideas because of my smart choice of function, so that should just be a t in there with it. And finally, we want to account for the fact that rather than being centered at a height of 0, we are centered at a height of 125 here. So our midline should be 125 out there on the end. So this, to me, looks like the equation that we should be using to model any passenger's height t seconds after they have stepped onto the Ferris wheel at its lowest point. Now let's go over into Desmos and try and find some values of interest associated with this equation. Now that we've identified the formula associated with our Ferris wheel problem, we'd like to use that formula in Desmos to help us identify some values of interest. We just identified that the height of any person on the Ferris wheel, t seconds after getting onto the Ferris wheel, will be given by this equation, and so I've entered this equation into Desmos. You should notice that I'm sitting at my home view on Desmos. That means from negative 10 to 10, negative 10 to 10 are my axes bounds, centered at 0, 0. Unfortunately for us, this isn't going to be a very good look at this problem. What we should recognize here is that we believe that this equation here will be taking in t values that are going possibly into the hundreds. We know that time is going to take 40 seconds for each revolution, and we're interested in looking at 1 and 2 revolutions. So I'm thinking that my input values, t according to my equation, but as far as Desmos thinks of it as our x-axis here, needs to go at least from 0 to 80, from 0 seconds to 80 seconds when I change my bounds. Additionally, I'm recognizing here that my output values, my heights, I know that on this Ferris wheel, I'm going to go from a minimum height of 0 feet up to a maximum height of 250 feet. So I'm going to go ahead and change my y-axis bounds, or what we maybe think of as our h-axis here, to go from 0 all the way up to 250. So I'm first going to change my window so that this is actually a reasonable graph for me to look at here. I'm going to go to my graph settings. And as we said, our x-axis, this should be handling our time values. I'd like these to go from 0 to, and let's just do 80 for now. We'll be able to scroll around a little bit, but this is going to say from 0 to 80 seconds. This will give us our first 2 revolutions on the Ferris wheel. Similarly, our y-axis values, or what we're thinking of as our heights, should go from a minimum of 0 up to a maximum of 250. Pretty typically here, I also turn off my minor grid lines. I think I'm going to do this. It'll probably just make this video a little bit easier to see, but often when I'm not interested in eyeballing values from the graph, the minor grid lines sometimes just kind of get in the way for me here. So I think I've done a pretty good job of making this graph. I always, when I build my window here, I typically like to zoom out and see if this feels like I think it should feel like. What I am seeing here, some things that I do agree with are, our graph is going from a minimum of 0. We're starting at the bottom of the Ferris wheel, so this is good. We're getting to the top of the Ferris wheel at a height of 250 feet, and then we're returning back to the bottom again after 40 total seconds. That's good. We know that 40 seconds is how long it takes for us to complete 1 revolution on the Ferris wheel. So as far as validating our answer to part A, I now feel pretty good about this equation. It seems to agree with all the information that we've set up about the Ferris wheel. Now we can start answering our questions for part B, C, and D. Part B is going to ask, during the first revolution, so only in time 0 to 40, at what time t is the person exactly 125 feet in the air? Now, one thing we could do is we could try and maybe zoom in here, and I'm zooming in until I see, oh, it didn't even do it for me there. I was looking for this height of 125, but what I think is going to be a pain for me is trying to eyeball some values that are out here. What I think is a smarter move here instead is to say we are interested in identifying when is the height 125 feet. So I'm going to add an equation over here that describes that to me. Height is given by h of t. I am interested in height being 125, and so Desmos is going to add a line of height 125 to our graph. Now what I can see is a couple points at which our passenger's height in red is the same as the desired height of 125 in black. I can see here the first couple instances of when this happens. It looks like 10 seconds in, 30 seconds in, 50 seconds in are all times that we're going to be at a height of 125 feet. But if I reference back to my original question, it was only asking about the first revolution. So I'm only interested in the first 40 seconds. So it seems to me like times 10 seconds and time 30 seconds are when we're going to be at exactly this height of 125 feet. So I think I'll go ahead and state those as my answer. 10 and 30 seconds appear to be the two times. And I'm going to make sure that I state this as a t equals so I remember what I was even just finding right there. For part C, I think I don't necessarily want this guy here anymore. For part C, we're now asking ourselves during the first 2 revolutions, so now within the first 80 seconds, at what time t is the person exactly 250 feet in the air? Well, I'd like to point out that this should be something that we can answer without technology here, and certainly part B as well. Recognize here in this Ferris wheel problem that 250 feet is your height when you're at the very, very top of the Ferris wheel. If I know that I start at the bottom at time 0, and if it takes 40 seconds to complete a revolution, then it certainly makes sense to me that I'm at the bottom at time 0 and 40, therefore I should be at the top at time 20. I should be at the top again 40 more seconds later, since the period is 40, at a time of 60. If we don't see this as part of the problem, we can still use our same idea here of saying, let's determine when is the height the same as 250 for our passenger. And so we can see, again, it's added an additional line for us, and it does show us when is our passenger's height, the sine curve, the same as the desired height, the flat line. And we can see that the 2 times that this does happen are going to be at time 20 and at time 60. If we go to look for another one, we see it's at time 100, which is past our first 2 revolutions. Each revolution takes 40 seconds, so 80 seconds is as far out as we were interested in looking. So it looks to me like the times that we've found are 20 and 60 seconds, at which we'll be arriving at a height of 250 feet. Finally, part D, which is certainly my favorite question to ask associated with this one here. In each revolution, for how long is a passenger above 220 feet? You should notice that 125 feet was a very clean value for this problem. It was exactly our midline. 250 feet was a very clean value for this problem. It was exactly our maximum value. But 220 feet is not some clean value associated with this problem. I know it's a height that we get to, but it doesn't seem to have any like special value relative to our sine curve out here, our cosine curve. So I'm going to do the same thing. I'm going to identify that the desired height of interest here, height, is 220. And what I want to know is at what times is our passenger's height, the curve in red, the same as the desired height of 220. What I also know here is I'm only interested in looking at each revolution. So I don't need to look across multiple revolutions. I think my answer is going to be the same for each of these. Each lap around the Ferris wheel should be the same. And what I can see here is it appears that we get to a height of 220 feet at times approximately 15.5 seconds and 24.5 seconds. But I'm not interested in when did we get to a height of 220 feet. I'm interested in knowing for how long were we at the height of 100 or 220 feet. So I do think that this little chunk of my graph is the very interesting part, but I'm not only interested in just these 2 numbers. Again, these 2 numbers are when were we at a height of 220 feet, not for how long were we at a height of at least 220 feet right here. When are we above the blue line? So what I think I can do here to find the total amount of time is to take the final time minus the initial time to get the total amount of time that we spend above 220 feet. So I'm going to recognize here that my final time was 24.504. 24.504. That's my final time. I can subtract this from my initial time of 15.496. 15.496, and Desmos will then report to me that it appears that 9.008 seconds is the total amount of time that we were at or above a height of 220 feet. So here are our 3 answers now that we've gotten from Desmos related to our model of our cosine function that we used for our Ferris wheel problem.